Alright, so what you see here is our fiber strain sensor under test. So Jack built this test stage. Consists of an aluminum block that slides back and forth. It can be adjusted with a micrometer screw on your left. On top of both of these blocks sits our fiber strain sensor. So it's a fiber optic cable. The Fiber Fabry-Perot cavity is right in the center. The micrometer screw, as you can see, pre-tensions the fiber and sits on a piezo crystal in green on your right. And that piezo crystal right now oscillates in length by about 120 nanometers at 5 kilohertz. So the fiber strain is modulated by 120 nanometers on a 3 centimeter stretch of fiber at about 5 kilohertz. So we are applying a strain of 4 microstrain. Alright, so anyway, the sensor is of course set up and locked and good to go, and we can see the output of the signal here on our oscilloscope. You can see it's a nice sort of full-scale signal corresponding to 6 microstrain. I'm sure you want to know just how low can we go. And what we're going to do now is we're going to reduce the voltage we apply to the piezo and reduce the strain modulation amplitude, still at 5 kilohertz.
That's 1 volt.
So we have 1 volt, that's 2 microstrain.
Half a volt.
Half a volt would be about 1 microstrain.
That's as low as we can go.
Yeah.
A tenth of a volt.
A tenth of a volt is actually the lower limit of our function generator, and that would correspond to, where are we now, 200 nanostrain or so, right? So yeah, we can probably detect, just go back to half a volt please. So half a volt, I think we can agree, we can easily detect, so that's above the 3 signal to noise level, so that would be about a microstrain. And I should say this is without any pre-processing. This is the signal straight from the laser control circuitry. So if you run this through a lock-in amplifier, or if you do some sort of cleanup of the signal, I'm sure you can easily get into the nanostrain regime.